Hello, everyone. Welcome to the next lecture. Again, in the past part of the lecture, we started with a circuit and we got its integral differential equation that we converted into an algebraic Laplace transform, very simple transforms. And based on that, we simplified the expression v of s over here at the bottom. And then we said that in order to get v of t, that was our eventual objective, we can just take an inverse Laplace. We put in the values of R, L, and C, and then we solve this partial fractions to got an expression for the V of t. So today we are gonna learn more about these partial fractions, how to take inverse Laplace transforms. So the idea is that in the circuits you may eventually get the Laplace transforms of the functions, the voltages, for example, the currents in different ways, and that may require different expansions of the partial fractions, right? We looked at one of the expansions, which was this expansion, right, where we can convert them into like a over one of the roots and b over the other one. So this is only valid when we have distinct real roots. So we're going to do more examples and we will see what will happen when we get complex roots or repeated roots. So we're going to take care of that in this part of the lecture, and the next part do a little more examples. So for the rest of the two parts, in this part we're going to do two example problems. In the next part we're going to do another three example problems. So let me get started. Slideshow from current. Okay. Right. So we are talking about inverse Laplace transforms. So another thing that I forgot to mention in the previous example problem that we were doing, or the previous derivation that we got of the parallel RLC circuit, once you were to solve that, or once you were to express that in the Laplace transform v of s, uh, that was a rational fraction, right? So what is a rational fraction of s? Rational fraction of s is if you were to transform the function f of t and find a Laplace transform of that function and convert that into f of s, right? You're going to have s variable in the numerators and the denominators, right? If you will convert that into kind of the polynomial way on the numerator and denominator, you're going to get some powers of s in the numerator and some powers of s in a denominator. So a proper rational fraction is when your denominator s powers are bigger than numerators, right? So for example, if the denominator has a highest power of s, for example, s raised to power 4, and the numerator is s raised to power 2 or even 3, this is a proper rational fraction. And on the other way, we have improper rational fractions where when your numerator has either the same power as the denominator or even the higher power as the denominator. For example, if the numerator and the denominator both are s power 2 or s power 3, or if the numerator is higher power than denominator. For example, over here you may have the highest power s power 3, over here the maximum power is s power 2, then that's an improper rational fraction. The previous example was a proper rational fraction because the expression that we got was in the numerator we did not have any s variable, so s power was 0, and in the denominator the maximum power we got a quadratic equation, so it was s power 2, so that was a proper rational fraction. Most of the things that we are going to do in the circuits, they will be rational fractions or proper rational fractions. Another important thing is most of these techniques that we are talking about, how to expand our rational fractions into partial fractions and solve them based on partial fractions, that makes our life easier when we do an inverse transform. Those techniques are only applicable to proper rational fractions and not to improper rational fractions. So we are going to, by the way, today in the next part of today's lecture, we're going to do one of the examples and we're going to see, okay, we have an improper rational fraction, so what to do. So let's keep it a secret till then. And let's do more examples, and we're going to realize that in all of these examples we are dealing with proper rational fractions. Okay, so very quickly again, as I was saying that in the previous example, in most of the circuit examples, that whenever you are finding unknown voltages or the currents, they are always going to be rational functions of s. So the idea is that you convert the time domain into s domain, simplify it, and then do an inverse transform from S domain into the time domain to find the current and the voltages, as we have been doing in the past. Okay, here are some of the rules, and we are going to talk about more rules. You have seen this thing, this rule before, right? Where we have distinct real roots, and these are also real roots for the quadratic equation. We have seen this kind of a case in the previous example, right? Where this could be any number, right? S plus a, s plus b. You can expand it as this: a s plus a, b s plus b. If you have a repeated linear root, so for example, if the root is something like this, s plus a square, and we're going to do an example today, something like that, right? So for example, k plus a square, the way to expand would be you're going to have a constant a, s plus a, then you're going to increase the power b over s plus a square. Similarly, if you have s plus a all the way to n, or let's say this n is 3, you can have one constant a1 or a b c d, any of the constants, right? One constant over s plus a, second constant s plus a square, all the way to s plus a power n. Now imagine that you may have even sometimes the multiplication of the distinct roots and the complex roots, right? So for example, this is the real distinct root. S is going to come out to be s over here, s equals minus 6, right? So this is a distinct root. But if you were to find the roots of this quadratic equation, it is going to come out to be complex roots, right? So you can expand this thing as square, and we're going to do, actually this example is going to become more clear, but this can be expanded into these two things. So the way to expand this partial fraction, this rational, proper rational fraction, you can expand this. The first term can be expanded by something like this: k1 is one of the constant, s plus 6, and then you can expand the other two roots of the quadratic equation, which were complex roots, right, by the constant. One is k2 and the other one is k2 conjugate, or a k2 prime, or asterisk, right? I can call it k2 prime or k2 conjugate. And we're gonna also do one of the examples, and then it is gonna become much more clear and easier on how to solve these, right? But this is how we can potentially expand these proper rational fractions. So you can call it kind of a cheat sheet, if you will. Okay, so let's do examples now. Here is another example. So let's see, this f of s was some maybe coming from a circuit, one of the circuits. It has some sort of a time domain equation that got converted into an S domain, and the expression comes out to be this. The very first thing that I want you to pay attention to, and that is, look at the S variables, right? So we have two S variables in the numerator. Once you're going to multiply this thing, the numerator is going to come out to be an S square polynomial with the highest S square value, S square variable. And if you're gonna multiply all of these things, open up all of these brackets and multiply everything, the maximum you're gonna come up with s cube. Since your numerator s power, your denominator s power is greater than the numerator s power, right? So this thing is gonna come out to be s cube squared, since your denominator power is greater than numerator power. So that is why this is a proper rational fraction, right? So let me write, f of s is a proper rational fraction. So the techniques that I was discussing on this slide, these are all for proper rational fractions, right? For proper rational fractions. There's a ways to solve the improper. Essentially, the way to solve the improper rational fraction, as we're going to realize in the later part of today's lecture, is we convert that into a proper rational fraction and then apply the same principles. Okay, coming back to the example. So this f of s is a proper rational fraction. So let's solve this f of s. The very first thing that I'm going to do is I'm just going to expand it, right? So I have 96 s plus 5 s plus 12, 96 s plus 5 s plus 12 s plus 8 s plus 6, right? As I can see that in the denominator I have three roots, right? So I can convert them as k1 over s plus k2 over s plus 8 plus k3 over s plus 6. k2 over s plus 8 plus k3 over s plus 6. Okay, so in order to solve this entire thing, the way to solve this entire thing is following exactly the same process that we have done in the past. We're going to pick one root at a time, or one of these things at a time, one of these partial fractions at a time, right? Multiply both sides of the equations by the denominator of that partial fraction, and then evaluate it at that root. So for example, to find k1, we're going to find k1. To find k1, multiply both sides by s and evaluate at s equals to 0, right? So if I'm going to multiply the left hand side by s, I will be left with 96 s plus 5 s plus 12 over s plus 8 s plus 6, right? So this s will be cancelled out. K1 s times s plus K2s over s plus 8 plus K3 s over s plus 6. And I am going to evaluate both sides at s is equal to 0, right? All of these sides. If s is going to be 0, this is going to be 0, this is going to be 0, and I'm going to replace s over here on the left hand side, right? So K1 is going to become equals to 96 times 5 times 12, because s is 0, 8 times 6. So the value of the K1 is going to come out to be 120, okay? Now we are going to repeat exactly the same process to find K2. Find K2. In order to find now this K2, multiply both sides by s plus 8 and evaluate both sides at s equals minus 8, right? So multiply, I'm going to stop writing this thing. This is probably the last time. Multiply both sides by s plus 8 and evaluate at s equals minus 8. Okay, so if I'm going to do that, let me still show you the entire thing again. 96 s plus 5 s plus 12 over s plus 8 s plus 6 multiplying by s plus 8. So s plus 8 will be cancelled, and I have to evaluate this as s equals minus 8. Okay, so the first one term is K1 over s plus 8 plus K2 is s plus 8 over s plus 8. This will be cancelled, plus K3 over s plus 6 s plus 8. And then you have to evaluate this as s is equal to minus 8, right? Now, again, what is happening over here is once you're going to evaluate the left hand side at s is equals to minus 8, right? We are going to get 96 minus 8 plus 5 minus 3 minus 8 plus 12 minus 4 divided by minus 8 plus 6 minus 2 equals K1. When I'm going to put s equals to minus 8, this is going to make the first term, K1 term 0, K2 was over here, and K3 will become 0 as well. Again, if you are realizing it, when we multiply both sides by this, by a particular, for example, denominator over here, s plus 8, and then evaluate it, what we are practically doing is we are getting rid of all the other constant and we only remain with one constant. So this becomes much more easier to find the answer, right? So the value of the K2 is going to come out to be, if you were to solve this, sorry, this should be plus 4. Minus 72. Okay. Now let's find the value of K3. Find K3. I'm not going to write it, but you have to multiply. Here's K3. Here's K3. Multiply both sides. Multiply both sides by s plus 6 and evaluate at s equals minus 6. So once you're going to do that, so let me do that. You're going to get 96. S is minus 6, so minus 6 plus 5 is minus 1. minus 6 plus 12 is 6. S is minus 6. S plus 8 is minus 6 plus 8 is 2. And S plus 6 and S plus 6 should be cancelled, right? Because we were multiplying both sides by S plus 6. So this is going to come out to be your left hand side. And this should be equals to, again, the only variable that we will be left with, K3. So your K3 comes out to be equals to plus 48. Okay, so we found all the three answers. K1 is 120, K2 is minus 72, and K3 is 48. So let me write down all of these values in the f of s, right? So this was our f of s, and we expanded this f of s like this. So f of s comes out to be a over s, right? K1 over s. So K1 was 120 over s plus K2. K2 is minus 72 over s plus 8 minus 72 over s plus 8 plus K3, 48. 48 over s plus 6. Okay, so this is nice. So what we are going to do is we can easily do an inverse transform now. Inverse transform. I already know that the Laplace transform of inverse of the Laplace transforms is unit step function, right? Inverse of 1 of s plus a is e raised to power minus at, and the step function, right? So I can convert this thing into over here. So I will get f of t, which is Laplace inverse f of s. 120 is a constant divided by, sorry, it is 1 over s, so 120 times a unit step functions, minus 72 is a constant. 1 over s plus 8 should be e raised to power minus 8t unit step function plus 48 e raised to power minus 60 unit step function, right? And again, this since we usually use capitals for the Laplace transform variable, I can use a smaller letter here. So my function f of t is going to come out to be 100 minus 72 e raised to power minus 8t plus 48 e raised to power minus 60 times a unit step function. Okay, so this is it, right? So this is how we can solve it. Again, you get this expression by solving a circuit, and then you have to solve this proper rational fractions into partial fractions, right, to make your life easier when you have to find the inverse transform. Let's do another example. This is more interesting. And in this example, let's first check that it's a proper fraction or not. Proper rational fraction. The maximum power over here is s1, and the maximum power over here is, once you're going to multiply s squared with s, you're going to come out to be s3. So 3 is greater than 1, so it's a proper rational fraction again. Right? F of s is a proper rational fraction. So we can potentially expand into partial fractions as well. Okay, I already know s plus 6, right? Let me find the roots of this quadratic equation, right? So find roots of s squared plus 6x plus 25 equals to 0. Once you're going to find the roots of this quadratic equation, the roots are going to come out to be minus 3 plus minus 4j. Right? So I can expand this entire thing as 100 s plus 3 over s plus 6 s squared plus 6s plus 25 equals let me rewrite this thing. 100 s plus 3 over s plus 6 times s plus 3 minus 4j s plus 3 plus 4j. And now I know that this is my new f of s, where I have kind of converted the quadratic equation into the products of the roots. So now I'm going to kind of expand this, right? Expand into partial fractions, okay? So 100 s plus 3 over s plus 6 times s plus 3 minus 4j, s plus 3 plus 4j. This should come out to be equals to, first one is k1 over s plus 6, right? This is a distinct root. Then we have again two roots, which are complex in nature, right? And we have seen that in the rules how to deal with it. I'm going to define k2, and then I'm going to define another one, k2 steric prime, which is a complex conjugate of k2. So s plus 3 minus 4j over s plus 3 plus 4j. So these are the two complex roots. There you go. Sorry. Okay. In order to solve this, again, I'm going to employ exactly the same thing that we have been doing, so I'm not going to do the details. In order to find k1, I am going to multiply both sides by s plus 6 and evaluate both sides at s equals minus 6. In order to find k2, I'm going to multiply both sides by s plus 3 minus 4j and evaluate everything at s equals minus 3 plus 4j. I don't need to do k2 prime because it is going to be a complex conjugate of k2 anyways. So all I have to do is to only find k1 and k2. Okay, so let's find again k1. Okay, in order to find k1, multiply both sides by s plus 6 and evaluate at s equals minus 6. Once you're going to do that, on the right hand side you're going to be only left with k1 and the left hand side is going to come out to be 100 s plus 3 over s plus 6 will be cancelled, the two roots, right, which are practically s square plus 6x plus 25 at s equals minus 6. Okay, so once we're going to do that, the answer is going to come out to be minus 12. So the value of the k1 came out to be minus 12. Okay, now let's find k2. In order to find k2, I'm going to again multiply both sides by s plus 3s, right? I'm going to do this thing. Minus 4j, and evaluate both sides at s equals minus 3 plus 4j. Okay, so once I'm going to do that again, on the right hand side, once I'm going to multiply everything by this and take this thing, on the right hand side, I'm just going to be left over with k2, right? So it's really solving on the left hand side. On the right hand side, I'm left with only k2, and solving for the right hand side, 100 times s plus 3 divided by s plus 6 times s plus 3 plus 4j. Again, because you were multiplying both sides by this term, right? So this term will be cancelled out. And you are evaluating at minus 3 plus 4j. Right? So if you're gonna evaluate this thing at minus 3 plus 4j on the numerator, you're gonna be left with 100 times 4j minus 3, and minus 3 will be cancelled out. On the denominator, if you're going to solve this, you will be left with 3 plus 4j times 8j. Right? And if you were to further solve this k2 again, and you will get 6 minus 8j. Again, this is your k2, and similarly you can get k2 prime 6 plus 8j. So the good thing about if you have complex conjugate roots in the denominator in this partial fractions, and so you make one constant as is, and the other constant we will call it as a complex conjugate of that constant, right? K2 prime here. So you don't need to solve for that. By the way, if you're going to solve for that, you're going to get exactly the same answer, but you don't need to solve for that because this is going to be just a complex conjugate of this thing. One more thing, we can potentially, again, these are our complex numbers, right? So I can represent k2 in different forms as well, right? So for example, k2 can also be practically written as, this is a complex number, right? You can take a mod of k2. Mod of k2 is 6 square minus 8 square is going to come out to be 10. And similarly, you can find the theta, which is tangent inverse minus 8 over 6, comes out to be approximately 53.13 degrees. So you can write k2 in different ways. Another way to write that would be, for example, it should be 10 e raised to power minus j angle, 53.13 degrees. Another way to write would be, you can write 10, this is a magnitude, and here's a phase, minus 53.13 degrees. So these are another representations of k2. Similarly, k2 prime would be 10, and the angle would be positive, 53.13 degrees. All right, and this is negative. Okay. So I'm gonna use these terms to further solve these partial fractions and get an answer f of t here. Okay. But just saying that you can of course you can write these complex conjugates in the Euler form and in the other forms as well. All right. So let me expand the partial fraction again. All right. So you have f of s. All right. So f of s, again, the first one was minus 12. So you get minus 12 over s plus 6, right? So the first root was s plus 6, k1. Then you have k2. K2 is 6 minus 8j plus 6 minus 8j divided by s plus 3 minus 4j plus 6 plus 8j divided by s plus 3 plus 4j. Okay, so you got all the three terms here. You got k2, k2 prime, and essentially you are putting all the values into this equation. So once you do that, let's figure it out the Laplace transform. Laplace inverse of minus 12 over s plus 6, we have done that so many times now. Minus 12 will be this, e raised to power minus 6t, a unit step function. Right? Similarly, Laplace inverse of 6 minus 8j constant, s plus 3 minus 4j, right? So 6 minus 8j constant, 6 minus 8j. And then you can, this is the translation in the S domain. So you can write e raised to power minus 3 plus 4j times t u of t. And similarly, the third one is 6 plus 8j over s plus 3 plus 4j should come out to be 6 plus 8j times e raised to power minus 3 minus 4j t times u of t. Okay, great. The only problem is I wanna further simplify these complex numbers to come up with an expression for f of t which you can consider this f of t to be some sort of a current or the voltage in one of these circuits, right? So let me further solve these two things, and then I'm gonna come back and find the f of t. uh okay, so just give me 1 second. Okay, so I'm gonna kind of take both of these parts, and I'm gonna show that 6 minus 8j e raised to power minus 3 plus 4j t plus 6 plus 8j e raised to power minus 3 minus 4j times t. And the unit step is, we are gonna eventually, once we're gonna write f of t, we can take care of the u of t at that time. It's just multiplying in both of these, or in all of these factors, right? So okay, so let's solve for this thing. Okay, so this thing is I'm gonna take e raised to power minus 3t out. So I will be left with 6 minus 8j e raised to power plus 4jt plus 6 plus 8j e raised to power minus 4jt. Okay. I also know that one of the identities, if I have some sort of a constant, e raised to power j omega t plus the conjugate of that complex number, e raised to power minus j omega t, should be equals to 2 times of real part of a e raised to power j omega t. You can prove this identity as well. Okay, so considering this identity to be true, I can further simplify the above equation as e raised to power minus 3t times 2 real part of a, which is 6 minus 8j, 6 minus 8j times e raised to power j omega t, which is j40. Okay, so great. So we got this thing. Eventually you have to come back and put everything here, right? Let me put a static here. Okay, so I got e raised to minus 3t to real of this number, this entire number, 6 8 minus 8j e raised to power j40. Okay, so let me solve a little bit more. E raised to power for j4t, from the either formula I know that this should be equals to cos of 4t plus j sine of 4t. Okay, so let me first solve for this one. So I got 6 minus 8j e raised to power j4t should be equals to 6 minus 8j cos of 4t plus j sine of 4t. Since I'm only interested in taking the real part of this, take only real part. So if I'm going to multiply this thing, right, real part of 6 minus 8j e raised to power j4t is 6 cos of 40, 6 cos of 40, 6 times j sine of 40 will be taken out because we are only considering real part. Minus 8j cos 40 will be taken out as well. And the only other part would be left with minus 8j square. J square is going to come out with minus 1 sine of 4t. So this should be 6 cos of 4t plus 8 sine of 4t. Okay, nice. So I can replace this thing over here, and my next expression that is going to come out to be e raised to power minus 3t 2 times of this entire expression, right? 2 times of 6 cos of 4t plus 8 sine of 40 e raised to power minus 3t times 12 cos of 4t plus 16 sine of 40. Okay, nice. So I got this cos of 40 and 16 sine of 40. Okay, so before I go back and solve this, I need to solve for this term as well, which I'm going to do it on the next slide. Okay, so we are considering right now 12 cos of 4t. Sorry, my paper fell down. Okay, so 12 cos of 40 plus 16 sine of 40. 16 sine of 40. Okay, so this is our equation. I'm going to use an kind of an identity where we know that, for example, cos of theta minus phi equals to cos of theta, cos of phi minus phi or phi, sine of theta, sine of phi. Okay. So I am going to use this identity, right? R could be R cos of 40 minus phi equals R cos of 40 R cos of phi plus R sine of 40 R sine of phi. I'm going to take R common here to make this thing simpler. Right, so cos of 4t cos of phi plus sine of 4t sine of phi. Okay. And this is also R cos of 40 minus phi. Okay. I want you to compare this part of the expression to this part, right? I already have cos of 40. So can I write R cos of phi? I already have cos of 40, right? Can I write R cos of phi as 12 and R sine of phi over here is 16? 16, right? Okay, so if that is true, I got a new complex other formula, right? R cos of phi plus R sine of phi, right? So 12 and 16. So I can easily find an R magnitude, which is 12 square plus 16 square. It should come out to be 20. And similarly, I can do theta, tangent inverse, 16 over 12. The angle should come out to be 53.13 degrees. Okay, so this is nice. So you got this thing. I can replace both of these numbers now back over here. So I will get R cos of phi should be equals to 20 cos of 4t minus phi. I was interested in getting this angle, which is 53.13 degrees. Okay, so this is equals to 12 cos of 40 plus 16 sine of 40. Okay, nice. So I'm gonna put down this part over here, practically multiplied with e raised to power minus 3t, and then put everything back to the static, right? Okay, so I got my next expression is e raised to power minus 3t 20 cos of 40 minus 53.13 degrees. Okay. So my overall expression now f of t is Laplace inverse of f of s, the first term, which is this one, 12 e raised to power minus 60. 12 e raised to power minus 60 u of t plus, what is my And now I know that what I did over here is I kind of added these two expressions, these two, right? So the answer of these two expression is what we got over here, e raised to the power minus 3 to power this, right? So this should give you 20 e raised to power minus 3t cos of 4t minus 53.13 degrees, right? And u of t. So f of t comes out to be 12 e raised to power minus 6t plus 20 e raised to power minus 3t cosine of 40 minus 53.13 degrees u of t. Okay, so this is how the whole point of doing this entire exercise was to show you how you can find the partial fractions when f of s, or the Laplace transform of a function, has complex roots, has distinct complex roots. We have like another 2 or 3 more examples to do, including one of the improper partial fractions, improper rational fractions. So which we're going to do in the next part of the lecture. All right, with that, thank you so much. Have a great rest of the day. Thanks. Bye.